Hey everyone, in this video I'm going to walk through an acid-base titration problem with you. It starts by saying how many liters of 3.4 molarities of HNO3, which is a strong acid, will be required to reach the equivalence point. Oh, keywords here. Equivalence point, with 5.0 liters of 3.0 molarities of RbOH, which is a strong base. Okay, so in this problem I'm going to show you actually two ways to solve this. So first is the stoichiometry way, and the next is actually using the formula. So I'm gonna showing you the first is the stoichiometry. But before all that starts, actually, let me get my little whip it out here. So we have to write the balanced equation. Okay. So remember the titration basically just you use the given acid and base as the reactant and to produce the products and to balance out the reaction. Okay, so the reactants that the problem given to us is HNO3 and RbOH. Okay, so let's write it out. HNO3 plus RbOH. Okay, what is it will be produced? Okay, think about that. So there's an H right here, okay? Remember, 99% of the times when you have a polyatomic ions with an H in front of it, that is an acid, okay? So which means that it will donate its hydrogen ions and produce, not produce, but it corresponds with a conjugate base, okay? So this is an acid. And remember, there's an acid here, so this also OH in here must be a base, because OH just means the hydroxide ions. This is always going to be a base, like 99% of the times. Actually, I didn't met an exception right now, currently. So if you met one, please tell me and comment below. Okay, so which means that a base is gonna accept hydrogen ions or a proton. These two words are equivalent or interchangeably used. So which means that this will produce, like, this hydrogen will actually bound it with this OH. Okay, so this is gonna like accept a hydrogen actually from this acid. Okay, you see that? So then OH plus the H, what is it equal to? 2H and an oxygen. Well, that's an water. Okay, so that's a water element. So cool. So which means that this will be a water. So what do we left right now? Okay, so H right here and OH right here is getting cancelled out. So it will leave us to it will actually leave us to Rb and O3. Okay, remember Rb, like always put the positive charge element in front and the negative follows. Okay, so we balance this out, and we don't mind also write the state for each. So this is going to be an aqueous, also aqueous, but this, remember, water, liquid, and their products, aqueous too. Okay, so first step we done. Okay, so I'm gonna actually show you two ways to walk through this problem right now. First, let's do the stoichiometry one. Okay, so remember, when you're faced this, like when you're met this acid and base titration problems, always starts with the volume that they're given to you. Okay, so what is the volume that they're given to us? Okay, so take a look. We have the complete information. Like we have both liters and the molarities of this compound. Okay, so that means that we are actually going to start it from here. We're going to start it from 5.0 liters. Okay, so 5 liters of RbOH. Okay, so actually let me write it in this way. I think it would be probably easier to see because RbOH. So remember, like, in order to do a stoichiometry, we're always gonna find the mole ratios. Okay, so mole ratios, very important concept. You will use this to all of the rest of your chemistry life. Okay, so mole ratio. So, but in the question, they didn't give us any moles, right? We didn't see any moles. But remember the formula. So M is equal to moles over liters. Remember? Molarity, or also you can say that this concentration, they are the same thing. It's always going to equal to the amount of moles present and divided by the volume. Okay, and the volume unit is liters in here. So we have the 5.0 liters right here, and we have 3.0 moles. So molarities. So how do we get the moles? Well, to get the moles, you would just times these two things. So instead of use moles to divide the volume, you're gonna use the molarity times the volume to get the moles. Okay, so right here we have both the volume and the molarities, or the concentration of RBOH. So we can just directly plug in these numbers in the formula to get the moles of RBOH, which will be 5.0 moles of RBOH. Okay, so we have this. Now it's the key part. We can use this to do our stoichiometry process, which means that use this moles and to find what is the ratio between RBOH and HNO3. What is it? So according to our chemical equation right now. Okay, so take a look at this whole thing. So you can see that there's no there's no like 2 or 3 coefficients in front of it. Every single reactants and the products have the coefficients of 1, every single one. Okay, so which means that the mole ratio of these two reactants are 1 to 1. Okay, so very easy. 1 mole of RBOH is gonna correspond with 1 mole of HNO3. So what is it equal to? Well, we don't have to multiply or divide by anything, right? We're just like times 1. So that gives us the same answer, 5.0 moles, except this time is HNO3. Okay, really cool, right? Okay, so we're halfway done. So take a look. What is the problem asking for? This problem is asking for how many liters? Okay, liters. So we have to find the volume of HNO3. So we already find the moles. How do we find the volume? Well, they're given to us 3.4 molarities of HNO3. What does it stands for? Or what does it like implies to? Well, remember I told you before, moles equals molarity equals moles divided by liters. This formula, really, really important. We're going to use this all the time for all of like the titration problems. So we have the molarities right now, and we have the moles. So we can just directly plug them in, okay? Plug them into the equation. So right now we have to find the liters, right? So how do we find the liters? Well, before it's like, we can actually use the variation at the bottom, like for our previous solving step. So we already find like the moles is equal to molarity times the liters, right? So we can just divide it by both sides of divide both sides by the molarity. So which means we can get this, and the molarity in here canceled out. Liters is just equal to moles over molarity. Really cool, right? We have the formula right here. So right now just directly plug that in. So liters is gonna be 5.0 moles divided by, what's the molarity? 3.4 molarity, which is gonna give us 4.4 liters of HNO3. Okay, so we get our final answers in here, right? So super cool. So just summarize a little bit right here. We first have to write out the chemical equations, like the balanced out equation, and then in order to do the stoichiometry process, we have to first find the moles of the given, always look at the problems, like what is the reactant that they give us, like more information or sufficient information that you can directly plug that into a formula to find the moles, or like molarities or other things. Okay, so in here, that reactant will be RBOH. So then we just plug in the liters and the molarities into the formula and get the moles of this. And this time we're going to use the stoichiometry process, which is 1-to-1 ratio. We can get the molarity, the moles of HNO3, which is the thing that we want to find, the liters of. So right here, plug that into the formula, the same formula, but just a variation of it. Okay, there's a lot of variation chemical equations in the chemical class in that area. So just to be really flexible, like really comfortable to doing all this stuff. So we variate the equation a little bit and then re-plug in all of the things that we have right now, and then we can get the final liters of the things that we're asking for. Okay, so that's one way using the stoichiometry process, and right now I'm going to show you another way, and this way is actually works perfectly for every titration problems if the reactance is 1-to-1 ratio. Okay, so big warning here, it have to be 1-to-1 ratio. If it's like a 2 HNO3 and 1 RBOH, you cannot use this process. Okay, so it has to be like coefficients of all of the reactants have to be 1. Okay, so both of those have to be 1. So the formula that we're going to use for the second method is molarity of acid times the volume of acid is equal to molarity of base times volume of base. Okay, so kind of similar, right? So basically this formula works just fine for every problems that have the 1-to-1 ratio for the reactants. I see a lot of students every year, they're just like, because this formula is relatively easy, and if you like feel really comfortable with it, if you see a titration problem, that becomes your first nature to just directly plug those like numbers into this formula. But sometimes, like most of the cases, it doesn't work. But this is a special scenario which we can plug the informations directly into the formula. Okay, so what we're gonna do right here is we're gonna find which of these 4 components, which of these like 4 letters like really stands for in this question, in this particular question. So this HNO3, as I said before, we already know this is an acid because it has a hydrogen in front of the compound. Okay, so which means that this is an acid, and it given to us the molarity of this acid. So which means this value must be the MA. Okay, so MA is going to equal to 3.4 molarity. Okay, so what is VA? Well, VA is the unknown. We have to find it. Okay, so VA, I'll just leave it like question mark. And then what is MB? Well, this stands for the molarities of the base. So the base in here is RBOH, and the molarity it given to us is 3.0. So MB is going to equal to 3.0 moles. And last but not least is the volume of the base. So it will be 5.0 liters. Okay, so we have all of the information right now. So what's the next step? Just plug these in. Okay, so but before I do that, we have to like change this formula to make it like look easier and read nicer. So we're asked to find the volume of the acid, so we can change this by MB. VB divided by MA is going to equal to VA. Okay, so plug those data in. So it will be VA is equal to 3.0 molarity times the 5.0 liters divided by 3.4 molarity. Okay, so and then we can plug those into the calculator, and guess what? We get the same answer. So HNO3. Really cool right here, isn't it? It turns out it shows that these 2 methods in this case, in this question, we can use them like both like interchangeably. They both yield out the correct answer. And always remember the suffix. In this case is 2, and also remember that the second method, this formula only works for the 1-to-1 ratio. I'll just write it here. 1-to-1 ratio works only. Okay, so yeah, so basically that's all for this video. And this is a very like very typical one for the acid-base titration problem that you will be met, probably on your first lesson of titration problems. And later on, I will probably post more of the problems that you can see that you cannot use the second method in here, because the coefficients, the mole ratio is not 1-to-1. So 1-to-1 only works for MV equals MV in here. But I think in like 90 or 80% of the scenarios, you will met the reactants that have different ratios, different like coefficients, instead of like a 1-to-1. Okay, so yeah, so I'll definitely post these videos later, and I hope you learned something from this video. And if you like my video, please subscribe and leave some comments below. I would like to hear your thoughts. And okay, so that's all. Thank you.